So the phenoxide is resonance stabilized, and I just drew one resonance structure. We can draw additional resonance structures, others, where the alkoxide is not. So it's not as stable. So that is less likely to become the minus. Question?
Can you add different substituents to increase the acidity of the phenol?
Yeah, we'll be looking at that below. Okay? Yes. Very important with how substituents on the ring affect benzoic acids. Okay? Benzoic acid, right? We can also have substituents there. We'll look at that. But in general, or we can have acetic acid. Both of these, though, are carboxylic acids. Carboxylic acids are even more acidic. That's why we call them acids. pKa about 4 to 5. Okay, even more acidic there. Why? Well, the anion. It's resonance delocalized. Yeah, but so it was also resonance delocalized with phenol. The fact that this is more acidic implies that this is even more stable. Why is that more stable than this? You can actually draw more resonance structures here.
With the two oxygens?
It's because when you draw a resonance structure here, where are we putting the minus?
On a carbon?
On carbon, on carbon, on carbon. And delocalizing the charge to carbon, while it's something, is not great. Because carbon doesn't like it. It's like, hold on, I don't want all this minus. But over here, where do we delocalize the charge to?
Oxygen.
A second oxygen. And that apparently takes precedence over having more resonance structures. And very often students think, well, this has many more resonance structures. This should be more stable. That is an argument. It turns out it's the wrong argument. It's okay. Yes, it's great that you got to understand, though, that sometimes you can have two arguments. But then what's the winner? You have to have a winner. Well, then this is what we know is reality in the lab. So that means that this argument must not be as important. The main thing here is we're putting the charge onto another oxygen. That's why these are so much more acidic than phenols. But phenol is more acidic than something where you can't do resonance at all, because at least we can delocalize it onto another atom. It's just carbon. Okay, so know your trend there, your approximate pKa's. There is a list of pKa's in the back of the lab manual. It's always been there from Organic 1. Need to start running these a little bit more and more. Some of these we've mentioned. Because of this acidity, we have differences in solubility. A regular alcohol, now I'm going to put an R group here, not soluble in aqueous base by deprotonation. Because aqueous base means hydroxide. That's the strongest base you can have in water. Hydroxide is not strong enough to deprotonate a regular alcohol. Okay? Because if you look at equilibrium, the alcohol is 16, hydroxide takes an H, becomes water, that's 16. And it's not enough to drive your equilibrium. You have to have a difference of about 2 to 3 pKa. We've said that before. By deprotonation. The reason I add this is, yes, ethanol is soluble in aqueous hydroxide. But it ain't because it's being deprotonated. It's just because ethanol is soluble in water. So really, you're talking about larger alcohols here. On the other hand, phenol is soluble in sodium hydroxide. Because if you treat this with sodium hydroxide, right, you're going to get the phenoxide, I'll just draw it like this, plus water, right? How do you judge the equilibrium? Which side's favored? This is 10, this is 16, which side's favored?
The side with the weaker acid.
Side of the weaker acids. This is going to exist as this. And since it's an anion, it's going to be soluble in water. Okay? Phenols are soluble in sodium hydroxide. regular alcohols are not. This can actually be used as a chemical test. And some of this has been in the comprehensive spec problems. Okay? By the way, what's another chemical test that's in some of the comprehensive spec problems for aromatics? It's in at least two of the problems in the workbook. What was the chemical test?
The interaction with potassium permanganate?
Yes. Does it react or not with KMNO4? What does that tell you about the unknown?
It tells you if there's a benzoic H present off the ring.
Exactly. Yes. But this can be used to tell if it's a phenol or not. Now, of course, carboxylic acids are also soluble in hydroxide. Okay? Because this would be 4 to 16. And of course, 16 is favored over 4. Okay? Carboxylic acids are also soluble in bicarbonate. I'm not going to do numbers here, but it's a weaker base than hydroxide. Bicarbonate typically will not deprotonate a phenol. Okay? This is sort of some extra information. The textbook may not get into this because it's sort of getting into finer and finer details, but I'm just letting you know. Okay? Okay. Effective acidity. Effective substituents on acidity of phenols and benzoic acids. Basically, if you have a net electron donating group, that will make the phenol more acidic or less acidic. Nick? Donating group. We're looking at this becoming a minus. If that's a donating group, is the minus going to be more likely to form or less?
Less acidic.
It's less likely to form. This thing's beginning like, hey, you're pushing all these electrons towards me. I don't want to become minus. That's too much. It should be less acidic. And what's that going to mean for the pKa? Higher pKa, right? On the other hand, if we have a withdrawing group, again, we're looking at this. This will stabilize the minus. Pull electrons away. That's going to make it more acidic, lower pKa. All right? It's the same trend for benzoic acids. Let's look at some examples. With phenol being right at 10, what is phenol? 9.9 or something?
9.95.
Okay, roughly right at 10. Okay? Paramethoxyphenol, 10.2. Less acidic. Why is it less acidic? Because the methoxy is a net donating group. Okay? Same trends as for EAS. Minor differences in some over here, we'll see. Paranitrophenol, 7.14. Why? That's significantly different than phenol. Why? Because the nitro is a strong electron withdrawing group. But in addition to just withdrawing, we also have resonance. You can do resonance of the anion into the nitro group. And I think there's some examples on the next pages for you to do that as practice. Actually, what if we had 3 nitro groups? And these are all 2,4,6 trinitrophenol. pKa of 0.38. That's quite acidic. That's more acidic than benzoic acid. Okay? Why? There's 3 nitro. Okay? But this is actually called picric acid. It's so acidic it's called an acid. By the way, it's also explosive.
I was about to ask, is the hydrogen on the TNT also acidic slightly? Is those the toluene?
It's more acidic than toluene, but you're making a carbanion here. It's not as acidic as this. How acidic is TNT? That's a good question. you would expect some acidity. Picric acid, if that was a methyl, that'd be TNT.
Yeah.
Yeah. Picric acid is also explosive. Sometimes you may see picric acid salts, where this is the anion, and then you have some positive, maybe a positive nitrogen. And that would be the picrate salt of this amine or something. But such salts can be explosive. Look at this example over here. And compare it to this one. Why is that one less acidic than this one? But what? Clearly it's not. What's going on here?
It's more stabilized if it were in parentheses because the OH is a strong acid.
I agree, but that's really what we've already said. That's what the numbers tell us. But the answer is, why is that though? Why is it more stable? Or why is it?
Because you can't delocalize the negative charge into the nitrogen.
It's because resonance. Here you can delocalize the negative into the nitro, and again, you should do that. I think there's practice on the next couple of pages. You cannot do resonance. I don't know if you can see that. You got to do your resonance. But you do have withdrawing. Inductive withdrawing is different than resonance withdrawal. Okay? And over here you can do both. Question.
So it's basically like the same principle as NAS, where you need like a strong, like a group 4 pair ortho.
You could perhaps make that correlation, but it's a little bit distant from that. Let's look at some benzoic acids. So you see the trend there? Benzoic acids, I could show these like this, but put R group here. Now, all these are para, but the R group is defined here. Now, R usually means non-hydrogen, but you can say R being hydrogen for a table like this. If R is H, that's just benzoic acid. It's 4.2. If it's bromine, it's 4.0, meaning it's more acidic. Why is it more acidic with bromine? This is a bromine. What's bromine? Is it a net donator or withdrawer on a aromatic ring? It's a net withdrawer, group 3. So if this is a bromine, it's going to be pulling. If you got an anion out here, the bromine is going to stabilize it. Thus, the anion is more likely to form with bromine there. What if this is a methoxy? What is methoxy on the aromatic ring? What's its net effect? Net electronic effect. Donating. And so if you have a donator, is that going to help a minus form out here? No, it's going to hurt it. So it's less acidic. But hold on. Look at the one over there on the right. And compare it to just if nothing was there. Adding the methoxy makes it more acidic than benzoic acid. Why is that? Position matters. Explain this.
Again, just
No, it's not just resonance. Well, what do you mean resonance?
well, like, for example, the electrons in the O being meta allow for, like, if you draw the structures, you see that denucleation charge.
I'm not sure. I'm not getting what you're trying to say. The delocalization charge.
Is it because it's a carboxylic acid instead of a phenol that can make a difference? Because the way that the charge can go to the carbonyl oxygen instead of just the regular oxygen. Because
Or any carboxylic acid can do that, right?
it was just because how up on with the phenol, if it was para or ortho, it'd be more acidic, but when it was meta, it was less. But here, it was if it was meta, it's more acidic, and if it was para, it's less.
I reckon I'm missing the explanation of why.
Is it just because like carbonyl is typically a meta director, and it's more better at a meta position, or
Again,
with
You need more explanation of why. Saying something's a meta director really doesn't explain why. And I don't see the correlation. No, the difference is, if this is methoxy, we can draw a resonance structure of this into this and put anion right there. But here, you do resonance here, because we can do resonance here. The anion is not going to be put right there. Actually, if you do methoxy here, you can put these electrons all the way into the carbonyl. But if you do resonance here, you cannot move these electrons into the carbonyl. The answer is the methoxy here is conjugated with the carbonyl, but over there the methoxy is not conjugated with the carbonyl. You need to show resonance structures for this. It's not conjugated with the carbonyl. Thus, it's not affecting the carbonyl group as much. But why is it less acidic than if nothing was, more acidic than if nothing was there? Because it's not conjugated with carbonyl. Thus, it's essentially no resonance. There's no resonance with the carbonyl. Yes, there's resonance into the ring, but not carbonyl. Okay? But that's the resonance consideration. What's the inductive effect of the oxygen? Inductively, it's withdrawing. And apparently that's the major effect here, and that's why it's more acidic. Here it is. The fact that this is more acidic tells us what's the net effect of the methoxy here. Withdrawing. We can tell that from the number. And a number you can determine in lab. The methoxy is acting as a net withdrawer here. Why? Because there's no resonance into the carbonyl. And the predominant effect apparently is just the induction, the inductive withdrawal. Where over here, the methoxy is conjugated with the carbonyl, and the net effect is resonance. And resonance is a donation effect, and donation is going to make the acid less acidic. This can be used to determine electronic effects of groups. What if the group coming off the ring was an SN-Me3? What if the carbon was bonding to a tin atom? And tin is like carbon, so it makes 4 bonds. So the other 3 bonds I showed to methyl groups. What if it was bonded to tin? Would you expect this to be more acidic or less acidic? Well, let me ask you a different way. What if it was bonded to tin and the pKa was 4.30? What would that tell you about the electronic properties of the tin? Is the tin electron donating group or withdrawing group in there?
Donating.
Yes. If that's our number, which we can determine in lab, that tells us something about a novel group. It tells us about the electronic properties of a novel group. pKa's can be used to determine electronic properties of novel groups. Make sense? Or otherwise you're like, I don't know, I've never seen this group before. What does it do? You can come up with all types of theory. How can we test what it does? Get a pKa, and the pKa will tell you what it's doing. Right? Acidity of carboxylic acid. Aliphatic. Aliphatic meaning sort of saturated. Okay? Now, of course, we've got unsaturation in the carboxylic acid. The aliphatic is really referring to the remainder of the molecule, okay? Like acetic acid, 4.76, not quite as acidic as benzoic acid. What if we have substituents out here? You put a chlorine out here at 2.86. Why? Because the chlorine is electron withdrawing inductively. Okay? What if you put 2 chlorines? Even more acidic, right? What about 3? I just drew that one with the CCl3, yeah? Even more acidic. We're getting pretty darn acidic here, yeah? Okay? What if the chlorine is sort of more further out here compared to closer? Not as acidic. Why?
Further away.
It's just further away. And the withdrawing nature of the chlorine, the effect sort of tails off as you get further and further away. Yeah? Did we do some of this in organic 1? We did the same type of thing. Yeah. A little bit of review. What about an iodine? I don't think I give a number here. Let's compare it to there. Should this be more or less acidic than that one?
Less acidic.
Yes, it's withdrawing, but it's not as much as that, because iodine is not as electronegative. Be less acidic than that one. We would predict less acidic. On the other hand, what if that was a fluorine?
More acidic.
Yeah. And trifluoroacetic acid, like there, is like, pK is like negative. Pretty darn strong acid. Basically, if you've got a net donator, it's going to be, or net withdrawer, more acidic. Net donator, less acidic. Makes sense, right? How about this one here? Now that one I compared to the chlorine. This one should be more, let's compare these to acetic acid. That should be more acidic than acetic acid, right? Because the iodine is withdrawing, some. What about this compared to acetic acid? Just plain acetic acid. Is that more or less acidic than acetic acid? Donald, you got something more or less acidic? Why more acidic?
Just looking at the iodine, like it's a solid gel.
Okay, but compared to acetic acid,
That's just
okay? More? If I say less? Why less acidic?
Well, because the lone pairs could be donated for to stabilize a resonance, perhaps. I mean, like,
Explain how.
that was incorrect. I just think it'd be less likely to form an anion because of the lone pairs on the methoxide.
More or less acidic than acetic acid?
Yes. Less.
Less acidic?
Yes.
Why again? Well, if you're saying less acidic, that means you're saying that it's a donated net donated group.
Yes.
Why is it a net donated group?
Because there are lone pairs on the oxygen that can then be donated.
Donated how?
Resonance.
Okay. How? Draw a resonance structure. I'm going to continue on because I don't think it's possible. Is this lone pair conjugated with anything? What type of orbital is a lone pair in? sp3. There's no resonance here. There's no resonance. There's no p orbital here. There's no resonance. Okay?
So
No
it's
resonance.
the same as acetic acid then, right?
No. What type of effect does the oxygen have? It always has the inductive withdrawing effect. It's withdrawing, just like an iodine is withdrawing. The answer is yes. It's more acidic than acetic acid. Here's what I'm trying to get at. Is a methoxy a donating group or withdrawing?
I guess it's just a
It's a donator group on an aromatic ring if it's in a right position because there's resonance. There's no resonance here. There's no resonance here. So when you're out this weekend celebrating being off next week, you say, and somebody asks you, hey, is methoxy a donator or withdrawer? You'll say, well, it can be both. Depends on the situation. Okay? There's no resonance. It's withdrawing. More acidic than acetic acid. Okay? Basicity of anilines. We're going to do that here because we're familiar with the aromatics now and we can look at groups. So it seems suitable to do it here. We're doing some acid-base review. Okay? Aniline has a pKa of 4.6. What? Is this an acid? No, aniline is actually, it's a nitrogen. It's not acidic. It's actually slightly basic. I mean, most neutral nitrogen compounds are basic, so this one's only slightly basic. The pKa refers to the acidity of the conjugate acid, okay? Aniline is slightly basic. Why is it only slightly basic? Because the lone pair is conjugated. If the lone pair was not conjugated, it would be sort of a base. Amines are base. It's only slightly basic because it's conjugated. Now in organic 1, we said if the lone pair is conjugated, it would be non-basic. And that's usually true. I usually told you there's a couple of exceptions. Aniline has slight basicity. Because if we delocalize this, we draw a resonance structure and we start putting charge onto carbon. Minus charge. Carbon's like, I don't want this minus charge. So the delocalization is not huge. It's not great. Slightly delocalized. Thus it retains some slightly basic character. pKa is 4.6. This refers to the conjugate acid because we don't use pKb's in organic chemistry. Okay? But you got to know how a pKa works. If the pKa went higher, does that mean that this is more or less basic?
more basic.
Yeah, more basic, the pKa would go higher. You got to get that straight. Okay? Because the pKa is really referring to this. Now that's an acid. This will give up a proton. This pKa is similar to carboxylic acid. These have similar acidity. Carboxylic acid is about 4 to 5. That H there is about 4 to 5. Okay? Now this is much more basic. Because that's sp3 nitrogen. It's not resonance. Anybody have a pKa for that? It's in the table in the back. We've also mentioned it in organic 1, but of course a lot of times when we mention things, they sort of just fly by like at comments and stuff. I understand that. But we did mention it, and it's about what?
10.
Yeah, this is about 10. Okay? And so you see, it means it's more basic. What does that really mean? That means that this is what's 10. Compare these. That was what? That's about 5. Which one's more acidic? That one. That's more acidic. That means it wants to go back to here more. Why does it want to? Why would it rather exist like that as opposed to this one? Because in this form, it can go back to being resonance delocalized. Okay? We can jumble up numbers. It's hard to talk about these quickly. You need to just think about these when you have your coffee and what the numbers mean. The only thing I can do here is sort of tease you. Okay? We don't have time for a full explanation here. Let's look at some examples here. Of course, if we have electron withdrawing group, right, that's going to pull these electrons into the ring, make them less basic, lower pKa. We have electron donating. Well, then these electrons are not going to be moving so much more into the ring, and they're more available to react. More basic, higher pKa. Which one would you expect to be more basic of these two? This would be more basic, right? This would be less basic. Relative comparison. The stronger base of the two is this one. Because the nitro group here is doing what? Really pulling the electrons. Now, aniline can act as an acid. If it acts as an acid, we're talking about doing this, forming the anion here. Now, this is theoretically possible. It's rarely seen. But this is a different pKa. pK for aniline acting as an acid is about 28, meaning it's not that acidic. Right? So you do have to be careful when someone asks you, hey, what's the pK of aniline? You need to ask, are you talking about it being an acid or a base? If you're talking about it being an acid, it's 28. But if you're talking about it being a base, it's what?
4.6.
It's about 5. Okay? While we're doing acid-base, it's good to review an extraction process. How could you separate these 4 compounds in the lab? Well, we have to understand that 2 of them are acidic. 1 of them is basic, slightly basic. And 1 of them is neither acidic or basic. Just hydrocarbon, not neither. And we can separate things with 2 layers, an organic solvent and an aqueous. How can we make compounds move into the aqueous layer?
Make it an anion or a cation.
Make them charged, anions or cations. Yes. How are you going to make these 2 charged?
Deprotonated.
React with the base, deprotonate, make it an anion. So under basic conditions, these will go into the aqueous layer. Will this be deprotonated under basic conditions?
No,
How acidic is that?
not really.
28. It's way above 16. It's got to be below 16 to be deprotonated by aqueous base. And of course, that has a pKa like greater than 40. Number 4 is never going to go into the aqueous layer, no matter what. And so you can extract here. You can work through here. I'll let you look at this on your own. We looked at this in Organic 1. What are they first? They're separating here. They're separating 1 compound by extracting with bicarb. Remember what we said earlier? Bicarbonate will deprotonate a carboxylic acid, but it will not deprotonate a phenol. And so the bicarb just turns the carboxylic acid into the anion. It goes into the aqueous layer. The other 3 remain in the ether layer, if you're using ether. You can use other solvents for extraction, ethyl acetate or dichloromethane. Okay? So now we've separated out one. Now we can come back and add hydroxide to the ether. That will convert the phenol into the anion. It will then go into water. But the other two will not. Then how do you separate the aniline from the naphthalene? Now we want to bring in acid, and acid will make the aniline, which is a weak base, it'll turn it into an ion pair. Then it will go into the water, and this will remain in the ether. And so through the process, we've separated all four into four different flats. Now the ions you can get back to neutral. How can we get this back to neutral? We need to add a proton back. What's the source of a proton?
HCl.
Strong acid. Put the proton back on. And this may precipitate if you're lucky. Remember Organic 1, very first lab, we did acid base and you got precipitates. Okay. Equilibrium here. Well, this was about 5, right? Carboxylic acid. What's the acid up here? HCl. It's like -5. Which side's favored?
Carboxylic acid.
5. You see? Any strong acid is going to make the other acid favored. And balance this out, you'll have sodium chloride. But there you go, it's back in the neutral form. And it may precipitate if it's not soluble in water. And benzoic acid will. Forms a white precipitate that you can just filter by suction. Okay, so be reminded of your acid base extractions. I thought this handout had some resonance in here, but that was actually Organic 1. That's why this is largely review. Anybody remember a handout where there's some resonance, this type of thing in Organic 1? All right, we're doing resonance. Understanding that resonance stuff back over there when we're looking at the R groups. Got to be able to draw resonance structures. All right. And I would say all right, but I'm concerned that you need to practice on resonance structures. Again, this was done in Organic 1. You feel like you're good on resonance structures? And you can explain all that earlier stuff by resonance? Okay. There's a couple of miscellaneous things here. We'll be looking at acid derivatives, esters. Okay, ester is an acid derivative. This is a neat little table of different esters which have different smells. Esters tend to have good smells, fragrant, sometimes fruity smells. Used in perfumes, yeah. These are different ones, and it gives the smell there. But back on the front, and again, nomenclature video, the acid derivatives we'll be looking at are, of course, the carboxylic acid, ester, right? Where we have a R group on the oxygen instead of the H. This drug actually has a thioester, Flonase. There's one in the back of the handout that also has a thioester. That's where you still have the carbonyl, but then the other oxygen's been replaced with a sulfur. And we're not going to be looking at the chemistry of thioesters. But it just happens that two of the compounds I show you have thioesters. But those are acid derivatives. What is an acid derivative? How do you recognize, what's the definition of a carboxylic acid derivative? Well, I covered that in the nomenclature video. So esters, but also amides or amides. I say amide, right? Amide in Lipitor. Ambien is a tertiary amide, where this is a secondary amide. So we'll be looking at the chemistry of amides. But also nitriles, or the cyano group. It's an acid derivative, right? Oh, right. Once you watch the nomenclature video and you hear the definition of an acid derivative. Verapamil. Okay, test on Monday. If we brominated verapamil with bromine, maybe FeBr3, where might it brominate at? That's a traditional aromatic bromination reaction, right? We have two aromatic rings. Which ring is going to brominate preferentially?
The right one.
One on the right? Why?
Unactivated.
More activated for EAFs. I see three open positions on the ring on the right. Which position would you predict would be brominated?
The one paired to the top ONE, because it also has
You mean pair to this methoxy here?
yeah, right here. It's also ortho to the carbon chain.
Because this here is an sp3 carbon. These are not directed to the same place. Because this one ortho or para, so it's directing here. But this one is directing ortho or para, directing there. So these do not complement each other. Where does this one direct?
Ortho.
Ortho or pair, so it's directing here and here. So you do have two groups directing there, but only one of the groups direct here. So maybe we get rid of that. Reasonable? Which is better?
The one on the bottom.
Top.
I'd probably say here because it's less sterically hindered. This is between two groups. And so I'd probably go with that one I've got highlighted there. Have to be a little careful though. We got this functional group, and this attacks the bromine, right? Right? This attacks this bromine. We're going to bring electrons down, right? DAS mechanism. Got to be careful though. This is a pretty reactive nitrogen. You may have a little difficulty doing this reaction with that amine there. We don't often talk about that sort of side reactions. We focus so much on a single thing. With a complex molecule, you got to be careful. You can have other reactivity. Is the cyano group going to react with here? No. But there could be sometimes it might, and we will be doing chemistry of the cyano group. Okay, guys, have a good day. See some of you in lab? Yeah, anybody have any questions about lab? If so, you can ask here.